So basically, my name is Oishik Das. I am currently, my highest qualification is MSc Electronics. My current company in which I am working is TEGOT Technology from 2016. And the current designation where I'm working is PMIC testing and validation. So anybody know about PMIC? PMIC?
No, sir.
So it's power management IC. So basically what it does is it, what will I say? It manages the power in any device. Okay, so in electronics and electrical, we all know that the voltage, current is there, but above everything, there is one thing we need to take care of. It's the power, right? So the IC which my company works on is a power management IC. We also have ICs from radio frequencies and everything, but we also have radio frequencies and everything, but our main IC with which we are developing at the moment is a power management IC. We are trying to make a charger where the power management IC will work as a, as a switch. So I have been in the coaching profession for around 7 years and I've been teaching from class 9 till BTech and MTech. And the skills which I possess by working this 5 years, which I've developed, you might say, is circuit design and testing, instrument handling, resistive and inductive switching, low voltage testing, and low voltage and high voltage testing, Python and automation. Hello, can everybody hear me? Hello.
Yeah. Good process. It's a cleaning up process.
Yes, sir.
On.
So basically, do anybody have any question regarding what I just told you, or do you want me to attend the question after the presentation is over?
Yes, sir. No question for now.
Okay, so my response, if you talk about my responsibility, so basically we all have known in BTech, we have studied of a device known as transistor, and then we have also studied a device known as MOSFET, is metal oxide semiconductor field effect transistor. So basically they are basically made of silicon, but basically what we decided, or what our company has decided, is to work on GaN. It's gallium nitride. Has everybody heard of anything? Do anybody know about anything about GaN? GaN, gallium nitride. Anybody can say. If it's a no, you can say it's a no. I know. So basically, you have heard of the term known as silicon MOSFET, right? MOSFET, which is made of silicon. Have you heard of MOSFETs?
Yes.
Yes, sir.
Yeah, they are made up of silicon. But the problem of silicon is their mobility is not that high. We require nowadays, what an industry required is a fast device, but a power optimized device. Like, for example, if you have a charger should be a fast charger, but it should take or consume a very less power. So if it consumes very less power, then obviously our electricity bill will be very less. Yeah, right. So that's the main motive of an industry nowadays, to have a very fast device, but a very power optimized device. So GaN, or gallium nitride, is a sort of device which can provide us both. Silicon can give us a very power optimized device, but not a very fast device as compared to GaN. So a fast has very relative relative definition, that you might say this is fast, this is faster, but relative to GaN, what research says, silicon doesn't give us that fastness, Okay, silicon doesn't give us that fastness of GAN. For example, I can also share you an example. Like, do you have Xiaomi phones? How many of you people have Xiaomi phones or Realme phones? Anybody can say. And anybody has smartphones, right?
Yes, sir.
So am I audible to everyone?
Yes, sir. Sir, can I share the screen if you permit me? I have PPT.
Yeah, you can share the screen.
Okay.
Yeah, you can share the screen if you want. Okay, thank you. So I am de-sharing. Okay. Yeah, go to the next slide, Nikhil. So basically, what I was trying to say that anybody has a smartphone. Anybody, right? All of us have smartphone. Can press a yes or a no in the
Yes,
chat
sir,
box.
yes, sir.
So everybody
Yes.
has a smartphone, right? So basically, if you check the specifications of the smartphone, you will see somewhere it is written 16 nanometer technology, 7 nanometer technology, 22 nanometer technology. So what is that technology? What is that?
Channel length.
Gate length.
Okay, channel length or gate length?
Gate length.
Channel length.
Can't that be equal to? Okay. Okay. So anyone else?
Size of the transistors?
Okay. Anyone else? Anything else? Any answer? Any else?
That's I mean,
Any other answer?
practically, channel length would be somewhat less than gate length because of depletion layer.
Or practically, what you just said, I couldn't hear you.
So channel length it depends on depletion width also. No, so it varies. So we take gate length.
Okay. So okay, who is Nikhil? Can you draw a MOSFET? Yeah, an N-channel MOSFET by in the whiteboard. Can you just draw a N-channel MOSFET? You can just close this PPT because I will come to the PPT later. Just if you can, draw a MOSFET, an N-channel MOSFET. Hello, Nikhil. Can you hear me?
Yes, sorry, sir. I was muted. This one visible now, sir. This one.
Yeah, this is visible. Just if you can just open a whiteboard and draw an N-channel MOSFET because I think you are sharing the screen. I just wanted to clear up something.
Means on notepad. So I don't
Yeah,
have that
not notepad. You
software.
can open up.
I don't have that software, sir.
So you don't have Paint.
No. Okay, Paint. Okay.
Yeah, Paint. Just in Paint, draw an N-channel MOSFET.
Is it visible now, sir?
Yeah, to me it's visible. Is it visible to everyone?
Yes, sir.
Yes.
Yes, sir.
Yeah, you can you draw an N-channel MOSFET?
Yeah.
Can you can any one of you mute, please? I think there is some background noise coming.
This one gate.
Yeah, the top one will be gate. Yeah, now tell everyone. Okay, draw a channel. Okay, draw a channel.
Yeah.
Okay, so now everyone, can you please tell me which one can you call the gate, that 22 nanometer?
Just a second. This one will be length.
Wait, this. So which one, everyone? Which one? The gate length or the channel length? So in your phone, you see a technology, right? 16 nanometer technology, 22 nanometer technology. What is that? Is it the gate length or the channel length?
Channel length.
Okay, one has answered. Anyone else? Anything?
Channel length.
Channel
Okay,
length.
but here I can.
Channel length.
Okay, but here I can. Okay, but here I can see that that the channel length is equal to the gate length. So can't I say it is the gate length as well?
It is actually technology node.
Yeah, okay, that is technology node, but what is meant by a technology? These questions are asked.
If
These are very
technology
basic
node
questions.
is 65 nanometer, then we can draw channel length of 50 nanometer to 90 nanometer.
I'm not asking
Depends
that. I'm asking that if you are said
upon
that
the technology.
draw a 60 nanometer technology, will you be drawing a gate length of 60 nanometer or a channel length of 60 nanometer? 16 nanometer rather.
It is variable. It depends on the technology, how much we can draw.
How much you can draw? Okay. Okay.
If we are
So
for a
basic.
65 nanometer technology node, we can draw channel length of 50 nanometer to 90 nanometer. For low, it depends upon low, whether you are working for low power or high performance.
No. Okay, I am not asking that. I am asking what you can draw. I am not asking. I am asking if you are asked to draw a 16 nanometer technology. Okay. So what will you draw? A gate of 16 nanometer or a channel of 16 nanometer?
Channel.
Okay, so okay, I'm getting different answers. Okay, so basically what happens, the 16 nanometer technology, whoever has said it's a channel length, they are correct. Now a very important question. Like here, what I can see, I can see that the channel length is equal to the gate length, right? That is what is being drawn, right?
Yes, sir.
Yes, sir.
Yeah. So now a question might arise that if I'm saying that the channel length is 16 nanometer, why can't I say the gate length to be 16 nanometer? Right? We don't say the gate length to be 16 nanometer because there is one effect which you have studied, I think, in your electronics device physics, which is known as the short channel effect. Do you know that? Drain-induced barrier lowering.
Yes, sir.
DIBL, short channel effect. So what happens in short channels? The gate length is more than the channel length. So then what is that 16 nanometer technology? Is it the gate length or the channel length?
It's the channel length, sir.
Yeah, it's the channel length. So the channel length becomes L. If L is a technology node, then the channel length becomes L minus 2 delta L. That is, if I'm considering, if the source has overlapped the drain, overlapped the gate by delta L, and the drain has overlapped the gate by delta L, then I have to subtract that 2 overlapping right? Then I have to subtract the two overlapping. So that's the reason why the 60 nanometer technology and the 22 nanometer, whatever you see behind your mobile specification is generally the channel length. It's basically we use an NMOS because of the mobility of being higher. I think this is clear. Why we call the channel length, not the gate length,
Okay.
to be the technology. Yeah. Okay, that's one thing.
And
Now-
so
now coming to the-
will be applied now, sir. Means when voltage is
What?
zero. Means when voltage is zero, that
What?
means when the drain voltage is zero. So in that case, we measure that now, sir. Means,
So basically, the shorter the channel length, the less VTH, the less threshold is there.
yeah.
But there are other disadvantages as well. Like if you, so I will talk that later in one of my sessions, but let's just keep it in that mind that if I saying 60 nanometer technology, 22 nanometer technology is the effective channel length we are talking. That is gate length minus the two overlapping lengths of drain and source with the gate. Understood, everyone?
Yes, sir.
Yeah. Now the question is, I am saying that now a 22 nanometer technology, a 22 nanometer technology is very fast. On a silicon, it's very fast. Okay. Now, if a 22 nanometer technology is very fast, and as I already said, silicon does have the property of power optimization, then why are we going into GaN? Very important question. Silicon is already there, so why I am going to GaN? Because this 22. Okay, can anybody tell that? So 22 nanometer technology is very fast, right? Okay, and as I already said that it is power optimized, but still for faster devices we are going for GaN. Why?
High performance.
Anyone? Okay, anyone else?
Due to breakdown voltage, breakdown electric field of silicon gallium nitride is higher. That's why it is
Okay, that
used
is
in
one of the
power electronic
points.
devices.
No, silicon devices are also used in power electronics devices.
But
that they are also. But yeah, that's one of the
breakdown
points.
electric
Breakdown
field
is
is
one of the
higher
points.
for.
Yeah, that is true. Breakdown, but for that reason only it is not being used. Anybody else? Any other answer?
Sir, could you repeat your question?
The question is, I said that the silicon is power optimized, right? And it is also fast. The 22 nanometer technology, the 7 nanometer technology, even the 60 nanometer technology, the phones which are coming up, they are fast. Then why are we going into GaN?
The short channel.
Exactly. Good answer. Good answer. Good answer. I like that. The short channel. Yes. Yes, it's very. Who are you? Can I get your name, please?
Rahul, sir.
Great job. Good answer. The short channel effect. That's the main thing we are shifting into GaN. In GaN, there is no short channel effect. First advantage. Yes, silicon at 22 nanometer technology is giving me a faster device, but that 22 nanometer technology, that 7 nanometer technology, that 16 nanometer technology is coming with a trade-off. What is that trade-off? That short channel effect. That short channel effect, what is the disadvantage? I will come to that later, but understand that due to the short channel effect, the gate is losing control over the channel, which we can't let it happen. Why? That's again a question. Why we can't let the gate lose the control over the channel? Okay. So that's the reason why. Okay, I will come to this question later. Why can the gate lose the control over the channel? Let's keep this question for the end. I will ask this question. Just think, all of you. Okay. Now coming to GaN. This GaN doesn't have any short channels. First, and another thing which is a very advantage, that if I keep the channel length of a GaN, 130 nanometer, 180 nanometer, 154 nanometer, then also my GaN will work as fast as a 22 nanometer silicon technology. Understood, everyone?
Yes, sir.
Can you repeat? Repeat, please.
So I am also using the GaN as a 130 nanometer, 180 nanometer, 154 nanometer technology, but still getting the same speed as a silicon 22 nanometer technology, 80 nanometer technology, 7 nanometer technology. So this short channel effect is being removed by using GaN. Okay, understood, everyone? Yes,
Yes, sir.
22 nanometer technology is very fast, but it has a trade-off: short channel effect, SC effect, second order effect. That's what we call. But GaN doesn't have a short channel effect. We can use a GaN at
Sir,
130
I have
nanometer.
one question. Why they are called a short channel effect? Or why called a second order effect?
Short channel effect because the channel is becoming short.
सेकंड ऑर्डर इफेक्ट क्यों बोलते हैं सर उनको?
सेकंड ऑर्डर इफेक्ट इसीलिए बोलते हैं क्योंकि जो इफेक्ट होता है ना, उसका जब हम इक्वेशन निकलेगा, वो शॉर्ट चैनल इफेक्ट का जो इक्वेशन निकलता है आईडी का, वो मैं आपको बताऊंगा अगले क्लास में, या फिर जब मैं आपका कंटिन्यूअस क्लास लूंगा, उसका होता है वो इक्वेशन होता है, वो आपका इक्वेशन होता है सेकंड ऑर्डर, और सेकंड ऑर्डर इक्वेशन का जो रूट्स निकलता है वो कॉम्प्लेक्स रूट्स निकल जाता है, वो मैं आपको समझाऊंगा. ठीक है, ये सिर्फ आप याद रखिए. तो ये हो गया 2. अच्छा, सो नाउ या one. Okay, so where was I? Okay, so that's the advantage of GaN. I hope everybody is clear now.
Yes, sir.
Okay, so Nikhil, back to the PPT, please. Nikhil? Yeah, okay. So the responsibilities of mine I was going through. So our company have a power GaN switch where we apply a voltage at the gate and the signal is shorted or the output is shorted. So the different, okay. So basically what happens is that if we apply a pulse at the gate, the switch will, the device will switch. So if the voltage at the gate is greater than VTH, we all know that the device will switch, as MOSFET acts as a switch. So this is a very important concept you need to keep. I know many of you may know that MOSFET acts as an amplifier. MOSFET doesn't act as an amplifier. It can never act as an amplifier. You have read in many books MOSFET as an amplifier when it is used in saturation region, but I am telling you MOSFET can never be used as an amplifier. MOSFET itself is a switch. So a switch is being used as an amplifier by doing some manipulation. I will come to that in my classes when I regularly take your class, that MOSFET is never an amplifier. Okay, understood my point, guys? I know many of you may know that a MOSFET is an amplifier. MOSFET is never an amplifier. MOSFET is a switch. It will be manipulated to act as an amplifier. Okay. So again, so my second operation, so my second responsibility, that there is a designer team we have in our team, in our company. So what design they make, we need to validate that design. So when you tell the designer that yes, the design which we have made is according to the specs you have decided. If not, you need to rethink of the design. Our job, or a testing guy or a validation guy, is not to make a design, it's to verify a design. So what we need to use for testing and everything, we need to use DMM. What is a DMM? Digital multimeter. We need to use an oscilloscope because there are various transient tests we need to do. We need to use a function generator. Okay, we need to use a high voltage power supply. Okay, so these are the instruments we need to use. We need to use, again, I forgot to mention it in the PPT, we need to use PCBs. PCB is an integral part of our job. We need to design PCBs for testing. And the last thing, there are many responsibilities, but these are the few important responsibilities which you need to perform. So, so automation of the instruments is very important. I don't know how many of you know that every instrument which you use in your lab has an automated version. Do everybody know that? Hello? Do everybody know that?
Yes, sir.
That
No.
hello? No, right? So every instrument which you use, like a DMM or a function generator, everything can be automated using a code. When generally the code which many companies use, or many companies are using, are these lab views, but what we use is Python. Okay, so we can use Python to automate the code. So to automate the instruments, because manual testing takes time, and in industry you don't have much time. Automation. So if 20 tests can be done in 1 hour, so if 20 tests, manual testing takes 1 hour, then automation testing will do that 20 tests in 10 minutes or 30 minutes. So that's a huge time saving, because in industry time is very important. Okay, so then next slide please, Nikhil. Yeah, another very important skill which is very good to have. You can learn it in the industry, that's not a problem, but it's very important to have. Yeah, it's very important to have this kinds of skill, which is Excel. Because to analyze the data, you need to have an Excel. It can be Google Sheet. If you know Microsoft Excel, yeah, it's good to. Okay, hello, everybody can hear me?
Yes, sir.
Yeah, okay. So it's good to have.
Yes,
So
sir, you
to
are audible.
analyze the data. Yeah, to analyze the data, it's very important to have this skill. Just not to enter the data. There are various things in Excel. There are various things. It's an extra information I'm giving you. An Excel, a person who knows Excel can only get a job by knowing Excel. They don't need to know anything. So this is the weightage of an Excel. Okay. And a very important thing, a validation engineer and a test engineer should know how to debug every current and every voltage at every node. Okay, of the test bench, because they are the test engineers. They need to design the test bench. Designers design the circuit. Validation engineers design the test bench where the test will be done. For that also, circuit design is very, very, very important. Okay. Okay, next slide, Nikhil. Yeah, skills. So the skills required for testing are circuit theory, as I already told you, component working knowledge, or how does an inductor work, how does a MOSFET work, how does a capacitor work, how does a transistor work, how does a resistor work. This knowledge needs to be known. How does a DMM works? So you put 2 knobs of your DMM against 2 knobs of your circuit. The DMM measures the voltage. How does it measure the voltage? Right? So you need to know that. How does the oscilloscope work? What are the components present in the oscilloscope? So instrumentation, in electronics, there is a part known as instrumentations and machines. You need to know that. Okay. Next comes very, very important, RC circuit. Okay, guys, RC circuit मतलब जी जान लगा दो इसको, क्योंकि इंटरव्यू में पहला जो प्रश्न आएगा वो आरसी सर्किट का ही आएगा. ये मेरा दावा है आपसे. Any question? any interview question will first ask you the first basic question: what is an RC? You need to know the basics of RC. RC घोल लो एकदम. RC अगर आ जाता है तुमको तो आधा 50% जॉब वहीं पे हो गया आपका. Okay. Next come MOSFET knowledge or the technology which the industry is using. It might be MOSFET, it might be GaN, it might be GAAS. So you need to know that. Okay, then Excel, as I already told you, it's good to have. And then connection concepts, series, parallel, star, delta. All these connection concepts are very, very important. Okay, so these are the things you need to know to be a good test and validation engineer. Next slide, Nikhil. Yeah, so guys, this is all from my end. So I think these are the important things you need to know. So one question I would like to ask you, which I told you that I will keep it for the end. Like I told you, right, that why I should have the control over the channel by giving an input at the gate. So can anybody answer me that question? It's fine, right? My channel is short, my VTH is very less, my device will switch very fast. So that's good for me. But I want the channel to be less long. I want the gate to control my channel. Why? Any answer? Anyone?
ID is a function of VGS. No, sir. If I lose control,
okay, Sam, so
over a channel, then how can I control my current?
So the channel is already forming, right?
Yeah, after forming also, I should
again. My question is, I don't think you understood my question. My question is, I have given a pulse, I have given a signal at my gate. My source is there, my channel is also there, but that channel is not being controlled by the gate. This is the situation. So what you are saying is that I am not giving a signal in the gate, but I've given a signal in the gate, but that signal is not controlling my channel. So that is drain barrier, sorry, DIBL, so drain induced barrier lowering, DIBL. Why?
Sir, pinch off voltage will occur if we start increasing VD. Then it will be saturated.
Okay.
Yes.
Okay.
At lower voltages.
Okay. Let me just give you an example. A small example.
Also controlling the channel instead of gate.
To control the flow of electrons.
Okay, so my question to everyone is, do you know everyone? Everyone, do you know diode?
Nikhil, just mute everyone.
Yes, sir.
Do you know diode?
Yes, sir.
Everyone, right?
Yes, sir.
Yeah.
Okay, so do you know, so can I use a transistor as a diode?
Yes, sir.
No, sir.
Transistor as a diode.
No.
Yes, sir.
No.
Transistor as a diode? Okay, can we use a MOSFET as a diode?
Yes, sir.
Yes.
Sir.
Okay. So in industry, no, not in industry, in everywhere, we use MOSFET as a diode more than simply a diode. Why?
The fabrication.
Both of them are diode.
Less power.
Both of
Fast. Hello. Hello.
Okay, less power, fast. Diode is also fast.
High input impedance.
Fabrication is the same also.
High input impedance. Diode also has a high input impedance if you check.
Fabrication is easy for MOSFET as compared to diode.
No, it's not at all true. Fabrication of a diode is way more easy. That point I can't take. The other points I can take, but this point is very absurd.
BJT is current controlled, MOSFET is voltage controlled.
No, I'm not talking about a VGT. I'm talking about diode and a MOSFET as a diode. But we use MOSFET as a diode more. We don't use a diode. Why? If you can give me this answer, you can also give me that why can't we lose control of the gate on the channel?
Because the depletion layer is fixed of bit.
No. Anyone else? Any other answer?
Sir, the
might be-
interference of
layout might
drain
be different.
electric field from drain side, we cannot allow the electric field from drain and source to interfere the electric field from gate.
So electric field is also there in diode. If we use a positive voltage, so we are giving an electric field, right? That's the reason why current is flowing through the diode. So again, that point is not justified.
Sir, the layout might be inconsistent having a diode.
Okay. Let me tell you. The answer is very easy. Basically, what that if we can use a component which we can control more, then that component we will be using more. Now, how can we control MOSFET more than diode? Now, see, okay. Now I have a diode. Okay. Nikhil, can you open up Paint and draw a diode?
Yes, sir.
See, guys, in industry, that you will be doing a lot of derivations in your academics. Those type of derivations are not required in industry. The industry is you need to catch where's the problem, what's the problem, and how the problem can be solved. That's it. That's what the industry wants. Industry doesn't want you to go to say 10 lines of derivations, 10 lines of these, that. Industry won't say. Industry will say that this is the thing. How will you improve it? For that, this kind of intuition is required. What I'm saying is all by intuition. That is very difficult. Okay. Okay. Draw a diode and draw a MOSFET. The circuit representation of a MOSFET. In channel circuit representation.
Symbol?
Not the. Yeah, you can draw a symbol. Yeah. NMOS. Yeah, NMOS.
Yes, sir.
Okay. Now, Nikhil, draw a voltage source at the P side so that the current flows through the diode.
What, sir?
Draw a battery so that the diode has a current through it.
Voltage.
Yeah.
Forward bias the diode.
Okay, draw a battery. Now you need to see that is design. Now this comes to design. You need to draw a battery in such a way that the diode gets a current. Now, how will you draw the battery? That is what the designers think. How will I draw a battery so that the diode gets a current? I don't need equations. I just need the diagram of the battery.
Okay. Just.
Because being in industry for 6, 5, 7 years, guys, equations are very much, to be very honest, you will also feel in this way. Equations, derivations are, very much, it will become very irritating. Because all is intuition. You will see a circuit, tell this is the voltage which will be here, this is the voltage it will be here. You don't need to do KCL, KVL every time. This is the voltage here, this is the voltage here. That's it. That all things has come from KVL, KCL, that is for sure. But this intuition, it will come automatically. Okay. Okay, good. So now the current will flow when the battery voltage is more than the threshold voltage of the silicon diode, right? Right, everyone?
Yeah.
Yeah. So now, okay, now Nikhil, draw. Now, how many batteries do you need in the MOSFET? You need 2 batteries, right? One at the drain, one at the gate. So draw those 2 batteries. This is not VGS. This is VG. Okay. This is VGS. Okay. So now see, very interesting thing here. So the current is flowing. Okay. So
Yes, you are audible.
okay. So in a diode, the current will flow when it is forward biased. Now, if I want, there will be, if I want no current, keeping the battery on, where can I do it in my diode? I want no current through that diode, but
No, we
I
can't.
want the battery to be on. We can't. But in a transistor we can. But in a
In
MOSFET we can.
MOSFET or BZ we can.
We just remove the gate voltage. Whatever voltage is there in the drain or the collector, no current will be going through that transistor.
Yes.
So a transistor or a MOSFET is a controlled device. So if I want, I can keep the power supply on, but when I will want, I will just take the current in the device. When I want. No, not when the device wants. So I am controlling the device, right? That's the reason why it is said voltage controlled current source. It is a controllable device. Diode is not a controllable device. When it is forward biased, it will flow the current. You can't stop the current until and unless you just remove the battery. Now, so many people that say, okay, I will remove the battery. What's the point? What's the point? Okay, I will remove the battery. But you need to understand that battery is not only connected with that diode, it may be also connected with 2 other parts of the design. So if I'm removing the battery, then I'm removing power supply to other parts of the design as well. That can't be done. Right?
Yeah.
Right,
got the
everyone?
point.
Yes, sir.
Yes, sir.
Yeah. So that's the reason why diode, transistor, or MOSFET, or GaN, or GAS, any device, any transistor rather, is more used as a diode than a normal diode. Where we have an isolated device, there we can use a diode, because the power supply is not affecting other power supplies or other devices. But when the power supply is interlinked, it's preferable that I use a transistor. Now that is the reason why. This is the only reason why we want control over the inversion layer. I, being an engineer, want a control over the inversion. So that's the reason why I want the gate, which is under my control, to control the inversion layer. So that's the reason why I want the DIBL not to happen. But it will happen, because that's a short channel effect. That's the reason why silicons are not used. Nowadays, we are transferring to GaN, because the control is more there. There are other devices as well. Dual gate MOSFET. There are other devices. Dual gate MOSFET,
BiCMOS.
MOSFET. Yeah, CMOS is not that kind. MOSFET devices are there, but still the DIBL is not being traded off. So this GAN is going, but there's a huge catch. This GAN is a very unstable device. We don't know the output characteristics of this GAN. In MOSFET, we know the output IDVT characteristics we know, but this GAN we don't know the output characteristics. Now you might say, then how are you designing it? Because every design, a designer does not have to know each and every page of a book. He has to know two things. One thing rather, the input and output characteristics of a device. That's it. That's all there a designer needs to know. If he can understand the input and output characteristics thoroughly, he's a brilliant designer. But the problem is in GAN, we don't have an input and output characteristics. Then how are we designing? So basically you need to understand a GAN is a switch. So either it will turn off, it will turn on. So just we need two states. We don't need the entire input output characteristics. So there are various assumptions which are made. Keeping that in mind, we are designing GAN switches.
So GAN not used for amplification.
No, amplification we can't use GAN, because amplification, I will let you know, amplification is in the saturation region.
Yes.
It is not the start and the end. It is in the middle. So we don't know what is in the middle of GAN. So how can we use it as an amplifier?
Okay.
Researches are going on. So let's see what happens. So this is what all from my end. So
Hello.
yeah, any questions you have, then you can shoot.
So that means GAN can be used very efficiently in the digital application, no?
Yeah.
Yeah, it can be used in a digital application, but now again.
It cannot be used in
If you have
analog
good
domain.
things, analog, it can be used in digital as well. More powerful, it will be in digital.
Yeah,
Now,
because
it
in
has
analog
other
we need
disadvantages.
that amplification saturation region. If it is not
Yes,
then-
you can tell that. Yes, you can tell that. But again, GAN is a very costly device. First, in industry, just theoretical power voltage current time is not sufficient. The cost is again comes into, because it's an industry, it's a business. Okay. So GAN is a very costly device. The silicon is a very cheap device. The silicon oxide, which is being formed, okay, is very easy to form.
Yes.
So it's very cheap. So hence, many companies are not using GAN. They are using silicon.
So then to overcome the short channel effect, what materials are using other than silicon at present in the industry?
No, the short channel effect is there. So maybe they are using, I am not very sure because I haven't worked in silicon much. I have a huge experience in silicon working in my project. I used in wafers as well. But the thing is that I think they're using MOSFETs. There's a dual gate MOSFETs where the control is much more. So see,
Okay,
you need
in
to
the
understand.
dual gate MOSFETs, what is the material? Is it silicon or gallium arsenide or GAN? What is the material?
Silicon.
Okay.
Why? Do
Then
you have
if
any
it
other
is,
answer? Then tell me.
If they are the silicon, then the short channel effect is not yet overcome.
Yeah, in MOSFET, the short channel effect do sometimes may happen. Who has said that will not happen? But due to the dual gate, the control of the inversion there is more. So the short channel effect is happening, but it is being compromised, or this is being overlooked by the dual gate effect.
Okay, by dual gate effect, we can overcome somewhat, not completely.
Yeah, not fully, because again, in industry, the money is a very important factor, right?
Yes. And nowadays the research is going on 5 nanometer. Then the channel, short channel effect is a very crucial, and the leakage current is also no more. So how to?
Yeah,
how
leakage current will be there. So there are techniques which I will be sharing you or teaching you if I am given a chance to give you regular classes. But at this moment, I think up till now this is enough, I think. So just I just gave you the overall aspect of MOSFET testing and its validation, or again what I do.
Can we have your introduction slide once again?
So can you please share the slide, Nikhil?
Introduction slide once again.
Remember one thing, everybody wants to be a designer, right? But everybody doesn't want to be a test and validation engineer. But you need to understand, a test and validation engineer should be equally equipped with the design as well, because he's validating the design. Okay, so he needs to be absolutely equipped with the design. So let's not think that a designer is everything. The validation engineer is, you can say, a sign-off engineer is a validation engineer.
Then how different is verification
because he is signing off
from the testing?
Verification and testing is verification. See, verification and testing means testing. I'm testing the device. Okay, testing. I'm doing experiments to test the device. Now I'm putting the data in the Excel and analyzing. That is validation. I'm validating.
Okay, I mean, how different the verification? Like after the design, it will go for the verification. After that, it will go for the testing. Then how the verification is different from testing?
That you are, it's not like that. So what happens? The design is done, the layout is done, then it is sent into tape out. Few of the parts, like around 200 parts or 500 parts, are being sent to the lab. They are being tested and validated to check whether the fabrication is fine or not. The design is fine. Design will always be fine. Simulation will never give you the heating effect, right? The simulation will never give you the real-time effect, like change in temperature, change in pressure.
Yes.
That we need. So that we need to validate, right? That we need to test. So when few of the parts come to the lab, we need to test that. And after testing, after validating, if we say that the design and the fabrication process is okay, then the production happens. Then the production engineers produces or does the production.
So the simulations are done with the different PVTs, right? So there is a
different
simulations are done by designers.
Yeah.
Simulations. See, I would like to tell you. I would like to tell you that simulation is a very theoretical one. Okay, simulation doesn't give you the real life feeling. You
but
can
they do
design
exhaustive,
many things.
I mean, they do the exhaustive
you can design
simulations, right, on the different PVTs, right, on the corner PVTs, and they make sure that
yes, so that they do. That is again simulation.
Yes.
Again, that is simulation. That is not real life testing.
Okay.
Real life testing will be very much different.
Okay, then verification. When will verification come into the picture? After testing, you are saying?
Yeah, after testing, you can say. But testing, what does a test engineer do? It keeps the power. It keeps the chip in the socket. Okay, it keeps the chip in the socket and applies voltage current, measures the voltage or current or something else, whatever is needed. That is test engineer. Now, when the data comes, you need to analyze the data, right? That is again a job of a validation engineer. So a test and validation engineer are same. They do both the job. Understood? So guys, I think my session is over. So if you have any other question, then you can shoot me.
So when is this going to start? I mean, the course.
I'm not very sure. That Nikhil will be able to tell. Nikhil, if you can answer the question.
Yeah, guys. Based on your response, we are going to schedule classes, regular classes. Yeah, we will let you know. Okay. And Rajat sir will let you know, not me. Rajat sir will let you know.
Sir, in the course, you're also going to talk about the gas devices.
Yeah, if that is in the if we need to discuss that. So I, Rajat, and Nikhil will discuss the syllabus once. What needs to be done? What are done in the industry? What we need to teach?
Yeah, that would be really
Okay.
nice to cover the gas also, because ultimately, like, all the devices are now into play into the industry. So knowing about every device would be really helpful.
Yeah, that is also true. We will just
In
discuss
enhancing
this
the
and let you know.
skills. Yeah.
Yeah, okay. I think my presentation is over. So, anyone else any question?
Sir, from where we can get in-depth idea about
skills? That is all about intuition. You need to understand three things: an inductor working, a capacitor working, and a resistor working.
Yes.
You need to understand. I will teach you all. You don't need to worry. You need
So
to know the basics.
So number 4 slides, you mentioned the bullets. So all those will be covered, right?
Those are the skills you need to have. Yeah, and obviously I need to cover that to have you to have your skills, right?
Sure. Yeah.
What is the time for this session, sir?
It is in
Can
the
you tell?
evening. Classes are in the evening, like 6 to 8 or like that.
Okay, thank you.
And you can WhatsApp me for the registration. I am the admin of the group of all the groups. So you can just pinch me on WhatsApp. Any queries regarding anything.
Okay, and who is this? Is this Nikhil? Or can you send me the number?
No.
What is the name?
Yeah, Rajat this side. I am the admin of the group. You can just check it out.
Yeah, thank you.
So should we close the session?
Yeah, okay, sir.
Okay. Thank you, sir.
Thank you, sir.
Thank you, everyone. Okay.
Yeah, thank you.
Thank you so much, sir.
Thank you. Bye.
Bye, guys.